So hey guys, welcome to the channel CodeChef. If you want to learn competitive programming and get a good hold on DSA, this is the one-stop destination for you. Every week there are several videos which will enhance your skills in DSA as well as the editorial videos for the CodeChef's contest. So if you are new to the channel, then do subscribe the channel and turn on the bell notification. So myself, Chirayu Jain, I'm a CodeChef educator, and in today's video we are going to cover the Prim's algorithm. Right, all the basics will be covered of Prim's algorithm. This is the part of the minimum spanning trees playlist. Okay guys, so now let us start with the Prim's algorithm, right? So the end goal of this algorithm is also same that we have studied in the Kruskal's algorithm, right? We need to construct the minimum spanning tree, right? So if you have not watched what is minimum spanning tree, then the link is in the description. Kindly do watch what is MST, right? So the end goal is same as Kruskal's algorithm, but the approach that we are taking is quite different. It is greedy approach, but the steps that we follow is quite different from the Kruskal's algorithm, right? So let's get into the definition of it. So the algorithm uses the greedy approach, right? The algorithm uses the greedy approach to get the minimum spanning tree, but instead of adding the edges that we're trying to do in the Kruskal's algorithm, we will add the vertices this time, right? We're trying to perform some operations on the vertices and add those vertices to form the minimum spanning tree, right? So we need to add all the vertices, right? And in n-1 edges we try to make that possible with the minimum weight. Okay, so let's see how we can do this, right? Let us try to understand this with the help of an example, and then we'll formulate the steps that how we can form the algorithm of it, right? Okay, so here we'll take one of the vertices, right? We'll take one of the vertices and start from that vertex. Okay, so let us assume that we take this vertex 1, right? We take this vertex 1, and what we try to do is we try to form the MST from here, right? I'm starting from this vertex, and let me see what all edges I can take it, right? So whenever we take that vertex, I'll explore the edges that this vertex has, right? It has two edges, that is of the weight 4 and of weight 3, right? I'll try to make the connection with the vertex which has the minimum weight, right, of the ones which are connected to 1, right? So I'll try to make this connection. Okay, so what is the weight involved here? That is 3. Okay, now again I'll try to explore all the vertices that are present with these two vertices, right? All the edges which are present with these two vertices, right? So one has the remaining one, right? So this 2 is blocked, right? This is also included in the MST. This 2 is also included in the MST, and this vertex is taken, right? This edge is taken, right? So now what all edges do we have? So with 1 we have this edge of weight 4, right? With 2 I have 3 edges with weight 5, 6 and 2, right? So amongst these, what is the vertex, which vertex we can connect with the minimum weight, right? That is vertex 2. If we try to connect this that is vertex 4, right? So if we try to connect the vertex 2 with the vertex 4 with this weight, that is minimum amongst all these, because we have explored as of now till two vertices, that is vertex 1 and vertex 2, and we are trying to locate all the neighbors of these two vertexes, right? So 1 has the vertex 3 and 2 has all of the all of the neighbors, right? 3 also, 4 also and 5 also, right? So amongst these weights, which is the minimum one, that is 2. So we'll try to connect it, this edge, with the weight 2, and it is connecting to, sorry, let us indicate the different color, and disconnect the vertex 4 with the weight 2, right? So we have connected these 3 vertices as of now. Now the remaining part, now we have explored 1, we have explored 2 and we have explored 4. So how many vertices are left? That is 2 vertices are left, and how many neighbors that we can connect as of now? So we can connect the neighbors of 1, we can connect the neighbors of 2, we can connect the neighbors of 4. So right, so the neighbor of 4 is only 2, which is already there in the MST, so we need not to see any of the neighbors of 4. But the neighbor of 1 is still 3, right? It has the weight 4. The neighbors of 2 is 3 and 5, which has the weight 5 and 6, right? So we need to look at that. So what is the vertex that we can take, right? So amongst these 3, the minimum one is 4 that we can take, and it will connect 1 and 3. So we'll try to connect this. As you can also see, from 2 also we can get to 3, but the weight is 5. So obviously we'll greedily choose 4 because it will reduce the overall cost, right? So let us take this portion and connect to 3. And what is the weight that is involved? That is 4, right? So this is also done. Now 1 is totally explored, right? 4 is explored, right? Now only 2 only we can explore it, right? 3 also has is connected to 1 and 2, which are already the part of the minimum spanning tree, right? So we cannot do much of exploration from 3. Only the exploration required is from the 2, right? So 2 is connected to 5, right? So amongst these two, right, this is not possible, right? Because 3 is already taken, right? 3 is already taken. It is a part of the MST now. Anything else left? Only this 6 is left to connect to this node, that is 5, right? So we do not have any other option left, right? So we need to connect it to node 5 because we need to have all the vertices. And what is the weight involved here? That is 6. That is that we need to take. There is no option left, right? So this is the MST which is formed after this. You will see that all the vertices have been covered, right? 1, 2, 4, 3, 5, right? All the vertices have been covered, and this is the minimum possible weight in which we can cover all of these vertices, right? So what is the weight that is involved here? That is 4 plus 3 plus 2 plus 6, that is equal to 7 plus 2, 9 plus 6, that is equal to 15, right? So this is the weight of this MST, right? And you can see there is no cycle formed as well, right? There is no cycle which is formed, right? So this is how we construct an MST from a given graph, right? So you can now you are now able to construct the MST from the graph if you have been provided with the graph configuration. Now let us see the algorithm, how we need to step by step develop the algorithm of Prim. And in the later video, what we can do is we can just try to code that algorithm down, right? So now let us step by step understand what exactly are the points of the algorithm in Prim's. Okay guys, so now let us understand the Prim's algorithm pattern, how we can form that, what we have discussed in the example, how we can approach it, right? Basically the algorithm steps of the Prim's algorithm. Okay, so this is the same graph that we have taken in the example, and now we'll form the same MST using these steps, right? Step by step we'll follow the approach. So we have constructed here the 3, you can say, arrays, right? And the names are weight, parent and MST node. So what does this weight indicates is the weight which we keep on updating, right? Whenever we get to a vertex, and through which node we are getting it, the minimum weight that is obtained while going to that vertex is the weight that is kept in this array, right? So initially we'll take into the consideration that we are starting from the node 1, right? So we'll mark the weight as 0, right? Because we are starting in it, right? So this is the minimum weight that we can have it for node 1, and rest for all other node we'll keep the weight as infinite, right? That is the maximum possible value which we can keep for their for the approach towards that particular vertex, right? Okay, so this is about the weight array. Now the second one is the parent one, right? So initially we do not know the parent of because all the nodes are isolated, right, as of now. So we keep the parent as -1 for each of the following vertex, right? The third one is the MST node, right? So what is this, right? Whenever we take one node and we formulate, we come to the conclusion that okay, this node must be taken into the, like this vertex must be now must be taken into that MST. Now it is taken, so we'll update from false to true. Otherwise, if it is false, then this node, this vertex is now not taken into the MST, right? This vertex is not taken into MST. So if it is false, so we'll initialize all of this whole array with false. Okay, so this is the initial configuration that we have. This is the initial configuration that we have. Now let us start with the algorithm. So we are starting from node 1, right? So first of all, what we will do, the weight is 0, right? The weight is 0, and we are taking the node 1 into the MST, right? So because this is the first node, right, we have nothing to compare it off, so we'll mark it here as true, right? We'll mark it here as true. And the parent is there is no parent for this as of now because we are starting only with this, so we'll keep it as -1. So this is the initial thing, right? Now the thing is to explore its neighbors, right? So what are its neighbors? There are 2 edges which are connecting to the second vertex and the third vertex, right? So what is the weight of the second vertex, right? So how we can check it? So first thing is to check that whether this node is a part of MST or not. So when we go to this index, right, this second node is not a part of MST as of now. Okay, so this can be included in MST. Now the point is that what is from this one vertex, what is the weight associated to reach this node? That is 3. So is it better than the weight that we have at present? So at present we have infinite. Yes, it is way better, right? So what we will do, we'll update the weight here as well. So what is the weight? The weight is 3. We have updated the weight, right? Now what is the parent of this node? Now because we have updated the weight 3, so we need to keep a track of the parent, from which parent it is updated, right? So the parent is here 1, right? So we'll update the parent as well. This is a typical flow. So what is the parent? That is 1. Now this part is done. Now we have one more edge, one more connectivity between 1 and 3, that is with the weight 4, right? Same process we will do. We'll check whether this 4 is a part of MST or not, right? We'll not make it true now, right? We will not make it true. We do not know that there can be other possible option which could be better, right? So we'll just updating the weight and the parent right now. So now what we'll do, we'll try to look at 4, whether it is a part of the MST or not. No, it is not a part of MST. So we'll see the weight. The weight is infinite as of now, and the weight we are seeing is 4, right? So 4 is way much better than infinite, right? So what we will do, we'll update the weight. It is infinite. And the weight of 3 is 4, right? So now the weight becomes here 4. Also what we will do, we'll update the parent, right? So what will be the parent for this as of now? That is 1. Cool. We are done with the vertex 1. We have explored its neighbors, right? Now the point is which node we should take into the MST. So as of now we have only taken 1 as the node in our MST, right? We have only taken 1. Now next, which node to consider, right? So we'll take the node with the minimum weight possible and which is not included in MST as of now, right? So if we see this array, this weight array gives a track of which node can be taken into the MST, right? So when we go to this, we'll see that okay, 0, the node index 1, right, has the minimum weight, but it is taken into the MST, right? So we cannot take it. Now from the remaining, we can take the second node because it has the minimum weight and it is not included in this MST because it is false here, right? So we can take this node second, right? So now the node which is taken into MST is this one, node second. And what is the weight associated? That is 3, right? So what we will do, we'll mark it as true because this is not taken into the MST. We'll mark it as true. Now the similar process that we have taken for the 1, the similar process goes on, right? So what we will do, we'll keep the track of all the neighbors associated with 2. So we have 4 neighbors here, right? That is 1, 4, 3 and 5, right? But now let's start with 1. 1, we will look at it. We'll look at the MST node. 1 is already taken into the MST, so we cannot go and explore it again, right? So 1 is already taken into MST. Jump on to the next neighbor, that is 3. We'll take 3, right? So what is the weight associated with 3 here, right? So the weight associated with 3 here is 5, right? But here if we see that the weight that we have at present is 4, which is better than 5, right? So we'll not take this node. We'll not take this node because we have the weight which is much efficient than this 5. We'll not take it. Now the next one, that is 4. 4 is the neighbor of 2 and which has the weight infinite as of now, and also it is not part of MST, right? So what we will do, we'll update the weight here, right? So now the weight of node 4 becomes 2 and the parent of 4 becomes 2. So we'll update the parent as well, right? To include an MST or not, we'll see in the later part that whether a good option is available or not, right? Okay, so now the next part, the next neighbor of 2, the last one is 5, right? So the weight associated with this is 6, right? And we have infinite as of now, so that is better. And also it is not a part of MST, it is false over here, right? So we'll update it. That is, the weight now becomes 6 and the parent of 5 becomes 2. The parent of 5 becomes 2. So that is done, right? That is done now. Okay, so the exploration of all the neighbors of 2 is now completed. Now what we need to do? Again, the step, we need to traverse this array and look for the minimum possible weight which is not of node, which is not in the MST, right? So we'll keep the track. The minimum is 0, the minimum is 3, both are taken into the MST. Now the remaining one, right? Also the less than 3 is available now, that is 2, right? So we'll take the 2 and it is not included in MST. So what we'll do, we'll mark here as true. Mark here as true, and now node 4 is included in the MST. So we'll construct one more, that is this 4. What is the weight associated? That is 2. So it is now coming into the MST, right? Again, we'll explore all the neighbors of 4. Now what are the neighbors of 4? Only one single neighbor, that is 2, right, which is already a part of MST, nothing else. So then we'll not explore it. Only because the 2 was already the part of MST. We can track it from here, right? We can track it from here that it is already a part of MST. So we'll not explore it. So that part is now completed, right? Okay, so now let us take this node, that is 3, right? Because it is the next minimum that we have, right? The weight is 4, right? So it is not taken into this MST, right? It is not taken into this MST. Now what we will do, we'll take it into this MST, right? So this node also will take it into this MST, right? So if it is associated with any other node, that will get through the parent array, right? After this, the final parent is formed, right? So when we look at so we'll update here, that is true. Okay, so when we look at both of its connectivity, that it is connected to 2 and 1, both are already the part of the MST, right? So there is nothing which can be explored new, right? Both are the part of MST now, right? Okay, so now what is the remaining one? That is 6, this one, right? So the 5 now we will explore and mark it as true, and the node which is associated with the 5, that is 2, which is already a part of MST. It's already a part of MST. So there is nothing which is yet to be explored from 5. There's nothing like that, right? So now when we look, this is the complete structure which will be formed after the exploration, right? Now what do we look? How will form the MST? This is not the MST. This is, you see the there is a disconnectivity over here, right? This is not the final MST which is formed. So how will form it? With this parent array. With this parent array we will form what is the MST. How we can form it? Right, starting from this particular node, because this node 1 we have taken for the initial start, and there is no parent which is associated with this node, right? So we anyhow need to keep it, right? So right, starting from the second node, what we will do, we'll track the parent. So with the node 2, what is the parent which is associated? That is 1, right? So with 2, 1 is associated and the weight is 3. So this is included in the MST. With node 3, what is the parent? That is 1, right? With node 3 also the parent is 1. So we'll connect this, and what is the weight associated with it? That is 4, taken into the MST. With 4, what is the parent associated? That is 2, right? So we have already taken it, and the weight is 2, right? That part is done. Now with parent 5, now with node 5, what parent is associated? That is 2 again, right? So we'll take this, mark it here, and the weight is 6, right? So this is the final structure of MST which is formed. This is the final MST which is formed. So from the parent array we get all the edges which needs to be there in the MST, and the properties of MST are also satisfied. There is no cycle form. There are n-1 edges. You can see 4 edges there. There are 4 edges, and what is the minimum weight that we have? That is 4 plus 3 plus 2 plus 6, which is equal to 15, right? So this is what we got earlier also while understanding the example, and with this particular algorithm steps we are able to get the minimum weight, right? So this is what typical example of MST look like. This is what we will code in C++, right? So you have seen the examples. Now we'll cover all the cases which we have talked about here, and everything in the C++ code of this Prim's algorithm, right? So that will be covered in the next part, but this is the important video to understand how the Prim's algorithm works, right? So when we talk about the time complexity of this algorithm, right, so there are two approaches that we can take. One is the brute force approach, which gives us the time complexity of order of n square, and there is a way efficient approach which is including a heap basically, and which will give us the time complexity of n log n, right, plus some time complexity which are associated with the traversal of edges plus vertices. So basically in worst case we can consider that it will be nearly equal to n log n time complexity, right, which will include the heap data structure, right. So generally we'll code in the priority queue, just giving you some intuition about it, right. But if you want to code it with your own understanding, as of now you have understood what are the steps that will follow, it will give you more insights and more things to discover for the Prim's algorithm. So I'll prefer you once try to code it down, and in the next video we'll try to look at how we can finally code this Prim's algorithm in C++.